Okay, let us start from what we left off last time. This exercise, it's a string which consists of two different material. So the equation is still this. But v squared is equal to v1 squared for x less than L1 is v squared is equal to v2 squared for x greater than L1. So we similarly take y is equal to a of x times b of t. Then we get a double x divided by a of x times v squared of x is equal to b. Both sides are functions of x and t, but the left side is independent of t. The right side is independent of x. So therefore the whole thing is independent of either t or x. So it's equal to a numerical constant, and we write it as minus omega squared. How about if it's plus omega squared? You can study that. If you study that, you'll see that this part, the t equation, would give you an exponentially increasing or decreasing solution, and that's not interesting. So we only study the case where it's negative. And therefore B becomes harmonic. That's exactly the same as the usual case. What is interesting is the A part. So the A part gives us this equation. For the two regions, we have two different equations. And we also have the boundary condition that a of x is equal to 0 for x equal to 0. And a at L1 plus L2 is equal to 0 for x equal to L1 plus L2. Because the string is fixed at these 2 points. So if we use that to solve solve this equation, we get a of x is equal to a0 sine you can have a cosine also, but the cosine part must be 0 in order to satisfy the first boundary condition. Similarly, we can write on the next one, this is for x less than L1. For the right end, for the large x, we get omega over v2 times x. But we want to put the boundary condition in, and when x is equal to L1 plus L2, it has to be equal to 0. So it's obviously it's this. Because if we write it this way, when x is equal to L1 plus L2, automatically it's 0. In other words, the way we write it already has the boundary condition built in. Now we do matching. Matching 就是接轨，不是 match 是配对。是要在 L1 的地方，要 A of L1 等于 continuous。A prime of L1 等于 continuous。因为现在有一个 L1 for x less than L1 and x greater than L1, we have two different. We should make this equal to. So we get A0 sine omega over V1 of L1 is equal to A1 sine omega over V2 of minus L2. And if we take the derivative, we get A0 omega over V1 cosine of omega over V1 L1 is equal to A1 times omega over V2 times cosine of minus L2. The first equation is the matching of A. The second is the matching of A prime. Now let us divide these two equations so as to eliminate the A0 and A1. So I get, and we can eliminate the omega because we have omega on both sides. So we get V1 cotangent of omega over V1 L1 is equal to 1 over V2 of cotangent of L2 with a minus sign. This equation determines omega. I had not known this before, that if you have a string with two different kinds of material so that the velocity is different, you would get a very complicated equation like this. Let us take the case of L1 over V1 is equal to L2 over V2. V1 and V2 depend on the material. The book uses iron and aluminum. So once you have V1 and V2, you can choose L1 and L2 to be equal, such that this is true. In that case, this equation is you get 1 over V1 plus 1 over V2 times cotangent of omega V1L1 is equal to 0. So this is equal to 0. That's very interesting. You would get omega equal to a series of possibilities, and you have the integer n in it. But in general, so that's this case. In general, let's call this equation alpha. In general, alpha gives very complicated solutions for omega. So sorry, omega over我刚才写错了，这 omega over L2 给omega over V2 给忘了，这有 omega。这个 equation in general is very complicated, and you get the lowest solution for omega and the next lowest solution of omega may not have an integral ratio of each other. So I didn't know this before. I did not know that if you have a string which consists of two different material, if you pluck it in general, it may create sounds which are very peculiar and may not be harmonious. Any questions about this particular problem? One lesson that you can learn from this is that when you have a complicated equations, if you choose your steps carefully, the equations may become very simple. For example, here, the reason that we got to this simple result, relatively simple result, is because we chose these two very cleverly. If you did not do it, if you put a face in it, you get more complicated looking equations, and then things would not be so simple. So one thing that you should remember when you do an exercise or when you take an exam is choose your notations and your strategy carefully. If you do that well, things simplify. If you do that not well, things become more and more complicated. Okay, now we go to next chapter. The waves that we have been talking about are called transverse waves.因为它的motion 东西的 motion 的方向跟那个 wave 的 propagation 的方向是垂直的 but there are also longitudinal waves. And sound waves is one example. if I draw wavefront, these are called wavefronts. 比如说是 when sound waves travel, the air molecules vibrate at every point, but they do not all vibrate at the same time in one direction. So this is where the density of waves is high, and these are called wavefronts. These are the crests meaning maximum density. So this is maximum density, this is maximum density, and at the next moment, the maximum density would propagate, so it moves this way. A water wave is a transverse wave, not a longitudinal wave, but it has crests which move along. So these are sound waves are longitudinal waves. For example, the next 20 minutes, in the next 20 minutes, I'm going to derive the equation of motion for the sound waves. The book has a derivation. It's difficult to understand. What we are going to go through is much simpler once you have understood it, and it's more general. What we are going to go through is in contrast to what the book tells you. It's a bit like deriving Newtonian planetary motion by calculus compared with deriving Newtonian planetary motion by geometry. The derivation by geometry are always tricky and complicated, and in some sense useless, because you cannot use it in the future. While the derivation by calculus is, once you have understood it, is much simpler, and furthermore it allows you to make further progress. So it may look difficult, but actually it's simpler. So we are going to go through a derivation of a wave equation for sound. I think in high school you have all learned that the reason that there is sound is because there's longitudinal vibration of the air molecules. So we try to write down the equations. First, rho is density of air molecules. U is horizontal velocity. U 是一个 function of x 跟 t， 这 rho 也是一个 function of x 跟 t。这个 sound wave 是 along the x direction 在 move。第一个我们要写一个叫做 equation of continuity。rho 乘上 u 的 with respect to x 的 derivative plus rho with respect to time 的 derivative is equal to 0。这个 equation 非常 important， 这是in fact the way Maxwell developed Maxwell's equations in 1865, Maxwell derived Maxwell's equations. He had been working on that for several years, but it was in 1865 that he wrote down the right equation. The way that he wrote down the right equation is deeply related to this equation, only he was not talking about sound waves. He was talking about the conservation of charge. This is the equation of continuity, or it is the conservation of mass. It's the equation of the conservation of mass. While Maxwell wrote down the equation for the conservation of charge. And because of that, he introduced what is called the displacement current. And because of that introduction, he was able to derive what I told you once before already, that there is electromagnetic waves out of his equations. And he can calculate the velocity of electromagnetic waves from his equations. And that velocity turns out to be almost the velocity of the known light velocity. At that time, there was non-accurate measured velocity of light, and he noticed that the velocity of light is the same as the wave velocity out of his equations. So he said that the light is in fact the electromagnetic waves. That's a historical event in the history of mankind. So this equation is extremely important, and it's extremely easy to derive, because if I think of this motion, if I think of a column of air, and I ask, air is moving, so air mass is moving in and air mass is moving out. The question that I want to ask is the mass that moves out. The mass that moves out at B 是等于什么呢？等于这一点我叫 x， 这一点我叫 x 加上 delta x。In unit time, in time delta t 是等于 rho u a delta t at x plus delta x. U delta t in time interval delta t, this sheet moves to here. So this mass moves out. A U delta t is the volume. The volume 乘上 rho is the mass that moves out at x plus delta x. The mass that moves in at A in delta t is rho u a delta t at x. 所以呢 the net 就是这个减去这个，这个减去这个 of course 就是 rho u a delta t, the derivative with respect to x, turn on delta x. So per unit time, net increase of mass 是等于 d rho u a dx 乘上 delta x。不对，这是负的这个，因为这是出去的，因为这是出去的减去进来的 ，so 是 net decrease， 这个 net increase 是一个负的，那么这个当然就等于它的 net increase， 所以这就等于 d rho dt 它里头的 mass 是 a rho delta x 的 d dt。所以你把 a 跟 delta x 消掉以后，就得出来 equation。所以就得出 u x this equation is one of the simplest and fundamental equation of fluid motion. It says there's a conservation of mass. 刚才我们讲这是 one dimension， 假如是个 three dimension motion， 那就是它这个air mass can be moving in all directions. This is one dimension. One dimension space, one dimension time. 假如 three dimension space, three dimension time 呢，就变成 divergence of rho u。第二个 equation 我们要 write down 的呢是这个 force equation。刚才讲这个是 kinematics, it's only a matter of balancing the mass. We are talking about the mass moving out, mass moving in. The difference relates to how much mass is increasing inside. So that's what we did. Now we want to look at the pressure. For this, we again go back to the one dimension. We want to derive px is equal to minus rho u t. 在这一点有个 pressure， 在这一点有个 pressure， 这两个 pressure 假如是 the whole thing 是 uniformly moving, then these two pressures are the same, and so they balance each other. So therefore, what's inside suffers no force, and therefore its momentum does not change. But if the pressures are not the same, then you have dp dx. So the left side is the pressure difference, which is the net force on the inside. The right side is the momentum, is the increase of momentum. So this equation merely says the net force on this sheet is equal minus p is the net force. Because 因为假如这面的 pressure 大，这面的 pressure 小，那当然的 net force 是 negative. So this is the net force on that sheet, and the right side is the time change of momentum. So that's Newton's equation. Is everybody happy? Okay. What we have done is we have written down in one dimension, one space dimension, one time dimension, the two fundamental equations of hydrodynamics.这底下我们要 talk about small vibrations. Small vibration 的意思就是说 rho 跟 u is small. u 跟所有的 u 的 derivative and derivatives of u are small. Rho 呢不是 small, 可是 rho 的 change small. Rho is not small, but rho the derivatives, rho u, rho x, and rho t are small. 就你when there's a sound, the velocity, the density of air, it remains the usual density, but there's a small vibration, so there's smaller changes. So these are small. "原来的 rho 的 density 我叫 rho zero. It's not small. The pressure 呢，本来有个 pressure, P0 is not small. 可是 Px, Pt are small. Does everybody understand what I'm saying? And it's actually very obvious. So we are now going to process these equations, but neglect higher orders. We shall examine the two equations, neglecting second order terms. 就是两个 small quantity 乘起来，我们就不要了，只留到那个of course 留下来 zeroth order 的，留下来 first order 的 higher order 的都扔掉。我们看这变成什么？第一，我们看这个 equation， 这 ux 是 small。rho x、rho t 是 small， 这个 rho 呢 is equal to rho zero 加上 rho 的 change， 可是那个 change 那项乘上这个 u 就变成 second order， 所以我们忘记掉那个 change， 所以我在这写成这样。Is everybody happy？ 然后我们看底下这个 equation， 底下这个 equation 是 px。加上 rho ut 加上 rho t u 这个是 small， 这是 small， 这是 small。画箭头的都是 small， 这项我们可以扔掉了 ，because it's automatically second order。这个呢跟刚才一样，我们可以写成 rho zero。What we are doing is called perturbation theory. Perturbation 的 spirit 就是你把所有的 quantity 都分成各种不同的 order， 然后你一个一个 order 来研究。That was developed in the 18th century by many people, but especially Laplace and Lagrange, because it's very rare that you can solve an exact problem. Newton solved the motion of planetary orbits. That was very lucky. But if you talk about the three-body problem, you cannot solve it. There's no general solution. So and yet people had to study the motion of the planets or of the moon. So how do you do it? You develop the perturbation idea. So perturbation theory was developed greatly in the 18th century, and that still is being developed today. Hydrodynamics is a very complicated subject, and people use different ideas about perturbation. So perturbation, the spirit of perturbation is one of the pervading spirit in applied mathematics. In this particular case, the perturbation theory is very simple. So now what do we do about the P? So we write P as P0 plus delta P. And the Px therefore is d delta P dx. This is small first order. Now P 是一个 function of rho. When air vibrates, if there's local increase of density, then locally the pressure would increase. So let us assume that pressure is a function of rho. There's some subtlety about this, so we'll come to that. P is a function of rho, so therefore P of dP dx is equal to dP d rho dx. Now d rho dx is small. dP d rho 是 不 small， 所以我们如果 first order 的话，就变成这样。所以这个可以写成 dp dx d rho， 这叫做 compressibility 乘上 rho x， 这是 small。那所以这一equation就变成了 dp d rho 0， 这个与这 sound wave 没关系的，这是这个 pressure， 就是这个 mass 它的 compressibility， 你 density change 的时候，它的 pressure 怎么 increase， 所以这就变成了这个乘上 rho x 加上 rho 0 ut 加等于0。我再把刚才那个抄到这儿。These two equations now look very nice because first, this is a number. It doesn't depend on p. It doesn't depend on t. It doesn't depend on x. This is a number. This is a number. So these coefficients are all numbers, and what we have are these first order relations. Now, if I take the derivative of this one, I take u rho 0 utt is equal to minus dp d rho 0 rho xt from the first equation. Now from the second equation, this is equal to minus dp d rho 0 of rho 0 uxx plus. So we get utt is equal to dp d rho 0 uxx. This is our old friend, the wave equation, and the velocity. This is equation 18-3 in the book. Only it's written in a very peculiar form in the book. So that's the sound velocity. Let me say again, dp d rho is a property of the air. When you increase air density, its pressure increases. But now we want to introduce another concept. It's called adiabatic. In the sound propagation, in this analysis, when sound waves compress, when the sound wave propagates, there is a local change of density. So air is all the time being compressed and decompressed and so on and so forth. In that process, there is no heat flow. When sound waves compress air, there is no heat flow. No heat flow because heat flow is very slow. And when there's no heat flow, it's called adiabatic. The process is called adiabatic.所以这个 dp d rho， 所以 v 等于 square root of dp d rho。The dp d rho is adiabatic, is evaluated for an adiabatic compression. So 平常这应该写个 adiabatic。我们来试一下这 dimension 对不对？我们看 dp d rho dimension of dp d rho， 这个 notation 是 dimension 意思。这 dimension 是等于 what is the dimension of pressure？ Pressure 是 force per unit area。force per unit area 的 dimension 是这样的。Rho 是 mass per unit volume。Force 是 mass times acceleration， mass times length times time squared， 然后这个是 L， 然后这是 M， 这都消掉了，所以是 L squared over T squared， 所以是等于 V squared， 所以对的。你们去应该看一下 table 18.1，他告诉你这 velocity air 通常这个 v 是等于331个 meters per second， 在 water 里头，water 里头你要compressed water， 它是 very resistant， 所以它 velocity 是 much larger，velocity 是1482 meter per second。Steel 更难了，更难 compress， 所以它是5941。That they are increasing is perfectly in agreement with our daily experience. So, I want you in the last 20 minutes to learn two things. First, these two equations, these two fundamental equations. One is the equation of continuity. The other is the equation which balances force on one side and the momentum change on the other side. And I also want you to learn how to deal with such an equation by perturbation. Such an equation is very complicated. It's not linear. But by thinking of things in perturbation orders and just neglect the higher order terms, you get a linear equation, and therefore it becomes a wave equation. So that spirit of doing perturbation is something that you will be learning repeatedly if you want to become a physicist. Also, if you want to become an engineer. The phenomenon of interference you are very familiar with. You all know that if you have waterways, if you have two sources of waterways, then they interfere. So just read the book here. For traveling waves, like sound waves, the usual sound waves, there is energy generated by the motion. The small vibrations generate energy, and it flows. In fact, if you have a very large loudspeaker, you can feel the force coming together with the sound. And the book gives a sort of a half derivation. So I'll not go into that in detail. It's read that section. It's 18.27. Rho v is the velocity. Omega is the angular frequency squared. Sm squared is the maximum vibrational amplitude. The air molecules for example, in a loudspeaker, they are vibrating, and this is the amplitude of the vibration. There is a unit of sound volume. It's called decibels. The key formula is that the decibel scale is equal to 10 decibels times log to the base 10 of I over I0, where I0 is 10 to the minus 12 watt per meter squared. This is a very useful section for you to read, because then you would know what is meant by 30 decibel sound volume or 50 decibels. If you have a pipe, and the pipe, if both ends are sealed, closed pipe。你可以有个小洞在这儿，你在这里头吹，然后在这里头就开始 vibrate。The closed end means U 等于0。在这儿的这个 air 它既不能向前又不能向后，所以 U 等于0。Open end 它是 du dx 等于0。在那个地方有 maximum 的du， 有 maximum 的 u， 有 minimum 的 du dx。在这个情形之下呢，比如说是read the derivations of 18-38 and 18-39 for 不同的 pipes. We had roughly talked about this. Both ends closed, you get the frequency distribution is one kind. One end closed, one end open is another kind. Both ends open is a third kind. Suppose we have two frequencies, omega 1 and omega 2. With a small difference. Omega 1 minus omega 2. The omega 1 minus omega 2 is much less than omega 1 跟 omega 2。那么我们来问这个 sum 是什么 ？sum 等于 a cosine omega 1t plus cosine omega 2t。假如这两个的 amplitude 不一样的话呢，the phenomenon of beat is not as clear. It's most clear if they are the same amplitude. Then you get用这个 sum 这个 formula, you get 2 cosine omega 1 plus omega 2 t plus cosine omega 1 minus omega 2t. Because that's cos minus sin minus sin, and therefore the no 1/2. Sorry. No. Complete wrong. That's not what we are. Is equal to this is now 这个是一个 this is still almost the same frequency if omega 1 and omega 2 are about the same. This one, however, is has a very small frequency. 所以呢，这个的 frequency 是这样的。这个呢是乘上一个很大的 frequency， 所以其结果就变成这样。这个是 determined by 这个，这一部分是在里头 vibrate。从这儿到这儿，这是一个 frequency， 所以从这儿到这儿呢是 2 pi， 再 divide by 1/2 omega 1 minus omega 2， 这是时间。从这儿到这儿是 determined by 这个，这一个 cycle 是 2 pi， 所以2 pi divided by 1/2 of the difference 是从这儿到这儿。所以从这儿到这儿呢，是它的一半。在这个情形之下的 the way you hear is this beat. This is called beat. And so what is this frequency? So the beat the frequency 是等于 1/2 pi over delta omega。所以这个 beat frequency 是等于 f1 minus f2。这里有个 factor 2， 就是因为刚才这个从这儿要缩短成这个。beat。假如有个 sound wave 是在这儿在空气里走是这样的，这是这些 wavefront。你一个人在这儿听，假如这人是在动 then it's obvious， 假如这人向这面走的话呢，他听的这个 frequency 要比较大，要向那面走他听的 frequency 比较小。同样，假如这个 source is moving, then this whole thing has an additional velocity due to the motion of the source. So this is called Doppler effect. It was discovered about in the mid 19th century. And 这个 I'm sure you have learned it in high school. So the new frequency is equal to old frequency times new v plus minus v detector D 等于 detector， 这是 v plus minus vs s 是等于 source。I know that that you have all learned in the high school already. Suppose there's an object which moves faster than the velocity of sound. Then它在这一点走的时候，它出来这个 sound， 过了1秒钟以后，这个 velocity 走的，可是它已经走到这儿去了。这个 supersonic 的 airplane 就是这样，所以这就产生一个 shock wave， 因为在 next moment 它在这儿的时候，它有 smaller， 在这儿的时候，那么这个 angle 是这个 shock wave 的 angle， 这个 velocity 是 velocity of sound。这个 velocity 是 velocity of the airplane， 所以这个距离是 v source。在这情形之下，你看这是一个三角形，所以 sin of theta 是等于 v divided by v source。这个你再走1分钟，它如果再走1分钟，这个 plane 就变成这样，所以有个 wave， 这个叫 shock wave， 是这个 shock wave 是这样走出去的。when a very fast jet plane goes through, you can hear this very sharp motion. The hydrodynamics of shock wave is a very, very important subject. It's a subject which especially became important because of the war. Okay, we have more or less gone through the mechanics part of the book. Before we embark on the next chapters, these are thermodynamics and statistical mechanics. We have to review a little bit. What we have learned so far, something like 9 weeks or 10 weeks, consists of material that you already knew, most of you, from high school physics. But we have also learned a number of things which are not in high school physics. I thought about it this morning and I'm going to write them down. Moment of inertia. We went much more deeply into the subject of moment of inertia. Especially, we said that if you have a body, a complicated rigid body, it has three principal axes of inertia, and with three principal moment of inertia, I1, I2, I3, and I1, I2, I3 may not be the same. And that's a very complicated subject. Rotation of gyroscope. Planetary motion. Damped harmonic oscillator. String motion. Wave equation. Sound wave. Sound wave equation. 6. These 6 topics are what are usually not contained in high school physics. I know that some of you got a bit discouraged when you all of a sudden learn something which is a bit complicated. Okay. In order to know how you feel about this, 对于这个 moment inertia 那些 topic 很不 comfortable 的人举手。大家都懂了。I'm surprised. I thought many people feel uncomfortable about these 3 moments of inertia. 所以不要害羞，你要是没懂就举手，或者是你至少觉得这个好像有点点心里头看着就不舒服。我想知道大概有多少人，所以呢，是不是你们给我的印象是大家都这个 moment 呢现在都很简单了，都很懂了。我要请阮先生跟安先生帮我。我的问题是问，有几% 的人觉得这个 moment inertia 这东西是一个梗在那儿，不心里头看着就不太舒服。我问他们举手，他们都不举手，所以大家都很 happy 是不是 ？OK， 我看这个 rotation of gyroscope 那个更复杂了。这个的不 happy 的人比较多。OK，rotation of gyroscope 不太重要，你们将来会去学的。OK，planetary motion。大家对于 planetary motion 说是 ellipse， 是 parabola， 是 hyperbola， 那些 derivation 是很不 happy， 很不 happy 的人不太多是吧？Good， damped harmonic oscillator， 这个我想比较简单。Maybe some of you already learned it in high school. String motion 的 wave equation， 所以大家都很 happy 是不是？最主要的是 I want to know with these more advanced ideas which are actually very simple, you will be learning those things or things like that repeatedly in the next 3 years. So I'm only exposing you to them now. If you feel very uncomfortable, that's not good. If you feel a little bit uncomfortable, it's fine, because upon first learning something, it's natural to feel a little bit uncomfortable. But next time you see the same thing, you will feel much more comfortable. 我不知道是大家太害羞不肯举手啊，还是大家都觉得所有这些东西都学了很多，所以很 happy。OK， 我把这个问题改了一个少年。有没有人主张我们再花1个钟头复习刚才这6个 subject 里的哪一个 subject？ 你主张在哪个？我听不清楚。他们说前2个。前2个。有人主张。有人主张我们复习一下的 moment inertia 跟 rotation of gyroscope， 还有没有别人主张复习别的？他说最后2个，stream motion 跟这个 sound。OK， 所以我想大概是这样，就是 planetary motion 跟 damped harmonic oscillator 似乎大家 happier。damped harmonic oscillator happier 是不是因为many of you have learned it more or less in high school？ 没有。是不是有一些困难是因为，比如说是differentiate 这个 exponential 上头有个 i， 这就发生了问题。这个好像不是问题。Okay. If you ask me the most important things that of these subjects, the damped harmonic oscillator is very important because you are going to see it repeatedly. But I'm also sure that that's the easiest for you to learn. The last 2 subjects, the wave equations, that's very important, and you'll be seeing that repeatedly. So I'll be very happy to review that with you. The first 2 about the moment inertia and rotation of gyroscopes. The problem with the rotation of gyroscopes is very complicated because the mathematics is complicated and it's not completely solved. It's the general problem is just 2 complicated nonlinear differential equations. But the moment inertia is actually very, very simple. You merely have to get acquainted with matrices, and that you have to learn because you will be learning quantum mechanics, and if you do not feel comfortable with matrices, you cannot learn quantum mechanics. So, okay, so we'll review the moment inertia and review the stream motion and the sound motion. I think all of you are learning linear algebra, right? Have you gotten to diagonalization of square matrices? Yes. The discomfort that some of you feel about the moment of inertia is because you are not familiar with the concept of matrices. The concept of matrices is extremely simple, and it's just because you have not been exposed to it. And after you are exposed to it for a while, you will know that it's very simple and it's essential, both for physics and for mathematics. Okay, so we'll spend the next 10 minutes reviewing something about matrices.在 talk about moment inertia 的时候，我们要写一些 matrix。这 matrix 是这样的，是 mi 这是 xi yi zi， 把它写成一个 column， 然后这儿写成 xi yi zi， 写成一个 row。这一 multiply 出来的话呢，就变成 xi 的 square， xi yi xi zi， 这是 yi xi zi xi， 然后这是 yi squared yi zi zi yi zi squared， 这就是。然后你如果把它乘上 mi， 再 sum， 这个 matrix 是 deeply related to the moment of inertia matrix。那么这个the trick really 就是说，你可以转一个 coordinate system， 不用原来的，你随便找一个 xyz 你写这个，你不用这个 xyz 可以找出一个 system such that 这个 evaluation 可以变成diagonal 的意思就是这个 sum 出来这些都没有了，只有diagonal element。That's the fundamental point， 就是 no matter how the rigid body looks, there always exists one axis xyz such that using that axis this sum becomes diagonal。那么那个 axis 就叫做都是 around the center of mass， 那个 axis 叫做 principal axis of inertia。那么要证明那个的话呢，就只 depend on 一个简单的 theorem， 是说有一个 orthogonal transformation 把这东西diagonalize。什么叫做 orthogonal transformation 呢？假如这个 matrix 叫做 M， 就叫做 A， 就是这个 sum， 这个 sum 叫做 A。这个 sum 当然每一点都是一个很 complicated 的 sum。这个 A 呢，这个 A 是等于这 sum， 是一个 matrix。这个 A 呢，它有一个 diagonalization， 是 such that there exists an orthogonal matrix， 把这个写出来就变成0 0 0， 是这三个数目的 diagonal， 这是这 theorem。而这个 theorem 的 interpretation， 而它的 meaning， 就是说有一个 gamma， 这 algebraically 是说 there exists an orthogonal matrix with determinant 1 such that it can be used to diagonalize this. The meaning of it 就是说你在那个 system， 这就有一个 system 是 obtained by using the gamma to transform the coordinate， 在那个 system 里头，你做刚才那 evaluation automatically 是 diagonal， 所以那个 system 就是 principal axis inertia。所以这个观念最重要的就是这个 theorem。我现在要问的是不会证明这个 theorem， 还是对于这个 theorem 的意义不清楚？是这是 which one is the thing that's difficult to swallow？ 我想其实都很简单，只是 You have not seen it before. About how to prove this theorem, it's a trick. And in general, many proofs are unimportant because you don't need to remember the proofs. But in this case, it's good to know the proof because the proof teaches you something. Once you know this proof, you realize the geometrical meaning of what you do. What do I mean? 要证明这个定理，说是任何一个 symmetrical real matrix 都可以用一个 gamma tilde 这个 transformation 把它变成 diagonal。这个定理是怎么证明法呢？是先用 eigenvalue， 就是你先把这个 a 说是 a 减去 lambda i。Take the determinant， 你不知道等于零，那么这个等于零了以后呢，就出了所以就出了个 eigenvalue 的一个观念。然后呢，这个等于零的话呢，你 once 这个determinant， 这个 absolute 在这个意思就是 determinant 等于零就代表有一个 psi，there exists a psi， 然后这个 psi 呢就叫这个 eigenvector。这个观念极为重要，因为你要不懂这个的话，你根本不能念 quantum mechanics。这是 quantum mechanics 是第一步就要了解这个叫做 eigenvector。那么你有这个 eigenvector 呢，你就可以写成 a psi 等于 lambda psi。这就是这个。然后你把这个 psi 拿来，它有3个 eigenvector， 所以它有3个 eigenvalue， 所以有3个 eigenvector。你把3个 eigenvector 并排连起来就是这个 gamma， 这个观念极为重要，所以你再想一下，这样我给你们2天的时间，你们去把这个第一个题目就是为什么要有3个 moment inertia 跟3个 principal axis， 以及刚才讲的这个怎么证明这个orthogonal matrix 一定可以 diagonalize， real symmetrical matrix 一定可以 diagonalize， 你把这复习一下子。还有你复习一下子我们怎么 derive 的那个 string 是变成了那个 wave equation， 还有一个是怎么今天证明把那个 hydrodynamics equation 变成了 sound wave。你们每一个人 go back and review this, and if you have some fundamental questions, raise it next time. I think this review may be useful to many of you. 我忽然一下问你，你也许一时不记得你有什么地方 bother 你，你去想一下子，然后我们下礼拜讨论这个后天讨论这个问题。OK， 拜拜。